So this is our following slide. The second law of thermodynamics. It is impossible to construct a device that operates in a cycle and produce no effect other than transfer of heat from a lower body to a higher temperature body. So this is for refrigeration cycles. A refrigerator must have a work input. This work input should not be zero. And that's why it is seconds. This says that let me change this point here. So, and if it is not zero, if this is zero, this is not possible for a refrigerator to work in a way that you extract heat from a low temperature and reject heat to a higher temperature. This is the Clausius statement. I believe we went over the Kelvin statement already. This is the Clausius statement we studied about it last time. So we learned about the heat engine, Kelvin statement. Okay, let's move forward to the refrigeration cycle. So this is the schematic of the refrigerators and the heat pumps. So you must have to have the work input, and then there's a condenser. Heat is rejected at a high temperature in the condenser, and heat is being supplied to the evaporator at a low temperature. This is the schematic and the devices, what devices are being used in the refrigerator or heat pump. In the heat pump, the desired output, look, in the heat pump, the desired output is QH. So COP for heat pump is the desired output, which is heat supply divided by the work input. And COP for the refrigerator, the desired output is QL. This is the desired output divided by the work input. So this is the same thing I just mentioned here. COP for the heat pump is the, first COP for the refrigerator desired output is QL divided by the required input, which is WN. And the for heat pumps, we call them as a coefficient of performance because they are greater than one. Usually the efficiency is named with, which is the efficiency is usually less than one. That's why we call this coefficient of performance rather than efficiency. And the heat pump, the desired output is the heat supplied at a high temperature and the work input. And heat pump coefficient of performance is always one plus the coefficient of performance of the refrigerators. We can prove it. So We know that the coefficient performance of the refrigerators are QL over. Let me reduce this, is too big for me right now. And plus 1. As you can see, this is equal to coefficient performance of the heat pump, QH over WN. This is WN. Okay, these are the two formulae. So let's do one problem. It says that air conditioner produces 2 kilowatts cooling effect. So QL 2 kilowatts cooling while rejecting this much of heat. Heat is rejected in the refrigerator through the condenser. So, so this is the heat being rejected inside the condenser. So that's why we write it down Q dot H, which is 2.5 kilowatts. What is the COP of this refrigerator? Okay, or air conditioner. We know that Q dot L Do you guys understand this question? Please type in yes if you understood this problem. Okay, let us begin the next question. I see Sarah, Magali, Taylor, and Elsie. They have understood. So let's do the next problem. As I mentioned, this chapter is very easy. Just 2 or 3 formulae in this chapter, and that's it. And I would try to finish this week chapter 7. And if not, then I would make some videos. So the next week there will be no lecture, just you have to prepare for these 4 chapters. I would say emphasize on chapter 5, 6, 7. 4 you can take a look as well. So more questions will be related from chapter 5, 6, and 7. Okay, let's do this problem. A refrigerator used to cool a computer requires 3 kilowatts of electric power. and has a coefficient of performance. Calculate the cooling effect of this refrigerator. So we know that coefficient performance of a refrigerator is Q dot R, Q dot L over W dot N. And this is 1.4. I would just say this is Q dot L. This is your answer. Please type in yes if you understood this question. Okay, let's do this problem. Our food department is kept at -12. So this is the food department. This is Q dot L, this is Q dot L, this is W dot N, this is Q dot H, and by the environment is 30 Celsius. The total heat gain to the food department is estimated. So heat gain and heat rejected determine the power input to the compressor. We know that COP is Q dot L. W dot N is Q dot H. Q dot H is 4800. Q dot L is 3300. Is 1500 kilojoules per hour. In kilowatts, if you want to convert it into kilowatts, so you just have to convert hour into seconds. Hour is cancelled by hour, you are left with kilowatts. So it is 0.4. Now COP of this refrigerator is Q dot L, which is 3300. As you can see, this is 3300 divided by 1500. Do you guys understand this problem? Please type in yes if you understood this problem. A household refrigerator, problem number 646, 6-46. A household refrigerator that has a power input. So W dot in, it is a power input, 450 watts. And the coefficient performance of this refrigerator is 2.5 to, to cool 5 large watermelons. So number of watermelons, there are 5. Initially, okay, the 10 kilogram, the mass of each. So you have to change to final temperature. Initial temperature is T1, 20 Celsius. The final temperature is, you have to cool up to 8 degrees Celsius. How long? What is the time duration it will take to cool 5 watermelons? Watermelons can be treated as water. Specific heat is 4.2. Now, look, we want to know what is the time duration. So Q MC delta T. And this is for the mass is for watermelon. Final is minus 20 is initial. And if you solve for this is inside the refrigerator, okay? And this is inside the refrigerator. The heat being rejected from the evaporator. So this is 252 joules. And 1 second, I have to check it. Is it? Let's do this over here. 4.2. I'm sorry, this is. So this is per. Yeah, this is correct. 4.2 times 12 times, sorry, times 1 2. This is for 1 watermelon. This heat, and you have 5 watermelons. So the total heat rejected out of the evaporator is this kilojoules. And coefficient performance of this is 2.5. This is equals to Q dot L over W dot N. And W dot N is 450 watts. So now how do you go from QL to Q dot L? So we know that Q dot L is QL per unit time. So how much time would it take? So can I write down like QL per unit time divided by W dot N? Now let's see what is missing. So COPR it is 2.5. This is 2.5. So let me write down here 2.5. QL is 2520 into 10 to the 3 joules per second. Time duration. W dot in the question it is 450. So if you solve for this, do you get 2240 seconds? About 37.33 minutes required, about 40 minutes required to cool 5 watermelons. Do you understand this question? So we studied this one already, so let's see. Don't worry about this slide. This slide is explaining that if one statement is incorrect, the other one is also incorrect, or if one statement is correct, the other one is correct. So what happens in this case? So Kelvin, Planck, and Celsius statements are equivalent in their consequences, and either statement can be used as the expression of the second law. Any device that violates the Kelvin Planck, which is heat engine, also violates the clauses, which is refrigerators. A refrigerator that is powered by 100% efficient heat engine. So this portion is the heat engine. This portion is the refrigerator. So heat engine, Kelvin says it cannot operate until unless you reject heat to the environment. So without losing heat, and this is also not true, the equivalent refrigerator. I would not worry about this slide. This is just proof of concept. It's not that going to be used for our problem solving. So perpetual motion machine, any device that violates the first or the second law. A device that violates the first law is called P. Perpetual motion machine M1, which violates the second law, it is PMM2. So another thing, reverse, yes. This concept is important. So what is reversible and irreversible process? A reversible process that can be reversed without leaving any trace on the surroundings, and irreversible, a process that is not reversible. It is true from its definition, it is very clear. And some of them are quasi-equilibrium expansion or compression of the gas. This is frictionless pendulum. This is a reversible process. So let me show you in the diagram. If you have PV diagram, state point 1 to state point 2. Any process represented by dotted line is irreversible process. In reversible process, you you do not lose the heat or energy into the eddies or frictions, but in irreversible process you lose a lot of heat or energy to the in terms of like eddies or some frictions. When there are friction losses, then the process becomes irreversible. That's why it cannot come back to the initial state. And irreversibilities also happen when the so look, the friction is the major cause of irreversible processes. Unrestrained expansion, like if your car tire is busted, it is unrestrained expansion. Mixing of two fluids, heat transfer across the finite temperature difference, electric resistance, and so on. A reversible process involves no internal external irreversibilities and totally and internal reversible heat processes. So let me go show you the totally reversible heat engine, which is also known as ideal heat engine. The ideal heat engine, which the efficiency of which is maximum, is known as the Carnot heat engine or Carnot cycle. In this cycle, you see all the four processes are reversible. This is just a very highly imaginative case. In this, we are trying to explain that if you see all the processes are reversible, then this type of engine has a maximum thermal efficiency. And if I want to plot the PV diagram of this engine, you will show me, or you can see over here PV diagram of the Carnot cycle and the reverse Carnot cycle. Reverse Carnot cycle is for refrigerators. This is for a heat engine. You see, from 1 to 2, heat is being supplied at a constant temperature. Like if it is um, phase changing process, but this is we have to have certain amount of heat source and the heat supply to the piston, and piston moves to the bottom dead center, and then from here it moves further down. Expansion process. This is the expansion process. We call this as reversible adiabatic expansion, also known as constant entropy. You will see isentropic process. A reversible adiabatic process, there is no heat loss. Adiabatic means Q is 0. And then there is a heat isothermal compression. Heat is being rejected. This is isothermal, and this is reversible adiabatic compression. The major thing from this slide is that all the four processes, either refrigerator cycle or heating cycle, these four processes are reversible. Next slide, I'm going to show you Hey, they are telling us that the efficiency of irreversible heat engine is always less than the efficiency of the reversible. Efficiency for all reversible heat engines operating between the two reservoirs are the same. As you can see that the purpose of, just to explain to you that for reversible we don't lose the heat. For irreversible processes we lose the heat. And now I'm gonna show you don't worry about this slide much. This is important. This formula is only applicable for the reversible cycle. What happens that we can, that the ratio for the heat supplied to the heat rejected can be shown as the ratio of the temperature of the high temperature reservoir, low temperature. This is high temperature reservoir. This is the work output, and this is the low temperature. This is sink. This is source, and this is just an operation. So heat is coming from. So the thermal efficiency is the work output over the heat supplied. So if I write down the formula for thermal efficiency of the reversible engine, which is Carnot cycle engine, so I can write down QH minus QL over QH. Or I can write down like this. Or I can replace this ratio. I can replace this ratio by the temperature scale like this, because this is a perfectly reversible heat engine. That's why I can do that. Remember, this formula you cannot do for an irreversible engine. This is for only for reversible cycles. For irreversible, you will use this formula. For reversible, you can use this formula or this formula. Both are correct for a reversible cycle engine. Let me show you another slide explaining you the efficiency, thermal efficiency of a reversible. Look, a reversible, this is for any heat engine, the same formula which I just mentioned here. Any for Carnot, which is purely reversible cycles, and for reversible, this is just explaining to you that the efficiency of a reversible heat engine is 70%. It is still not 100%. Make sure that you understand that efficiency can never be 100% because it will violate the second law, Kelvin statement. Kelvin statement states that you must reject some heat. When you reject heat, the efficiency suddenly goes down below to 100%. So, but it is still 70%, which is much higher than the 45%, which is a real engine having some friction losses, some other eddies losses, and it is impossible to have a thermal efficiency greater than the efficiency 70%. You see my point? So this is just a concept. Your concept should be clear that thermal efficiency of a reversible engine for our irreversible, this is less than the thermal efficiency, it is equal to the reversible, it is impossible. Again, they are just the ratio, that's it. So again, now you can apply the same Carnot cycle refrigerators and heat pumps. You see, This is for any heat pump or refrigerators. But for Carnot, which consists of all the reversible processes, you just replace the ratio by the temperature. Kelvin's scale must be in Kelvin. You cannot use this ratio in Celsius. With this, we have finished this chapter. I want to solve a few problems before I go to the next chapter. So let's solve one problem. Okay, let's do this problem. From the work production perspective, which is more valuable? Thermal energy reservoir at 675 Kelvin, 325 Kelvin. So, or thermal energy. So let's see. Well, we know we want to find out thermal efficiency of the heat pump. 1 minus TL over TH. 1 minus. Let's find out this thermal efficiency. So we will compare both of these efficiencies. So efficiency of case B is greater. Efficiency case B is, so this we will prefer case B. Okay, let's do question number 18. A heat engine is operating on a Carnot cycle, means purely reversible cycle, has a thermal efficiency is 75%. The waste heat from this engine is rejected to the nearby lake. This is the lake at 60 degrees Fahrenheit. The temperature of the sink is 60 Fahrenheit, but we have to convert it into Rankine. And Q dot L, this is Q dot L, okay? Heat is rejected to the lake. Find out the power output of the, we have to find out the power, net power output. Find out the temperature of the source. Since thermal efficiency has been given, which is equal to 1 minus, I will say let's start from the basic concept. work output divided by the heat supplied. And the work output is not given. We have to find this out. Point 0.75 Q dot H. And you already know that the output power is also equals to Q dot H minus Q dot L. Okay. And if you bring this on the left hand side, 1 minus 0.75 would be, I'm just simplifying this. Q dot L is 800, so it is equal to 800 BTU per minute. So can you find out Q dot H from here? So 800, let me check in my computer. 800 divided by 0.25. It is about 3200 BTUs per minute. So this is the heat coming from the source. We have found Q dot L, we have found Q dot H, and we know Q dot H minus Q dot L, it is the work output. That is our first question. Q dot H minus Q dot L. And 2400, correct? How do you go from BTUs per minute to horsepower? Because our question is in answer is in horsepower. So we know that there is a conversion. So 1 horsepower equals 2545 BTU per hour. And our answer is in BTU per minute. Okay. How do you go from minute to hour? It's not difficult, just like 60 minutes in 1 hour. So this is now in BTU per hour. Okay. And now we know that this is in BTU per minute. So I can write down here, if I can write down 2400 times 60, it is BTU per hour. Now this unit, I'm going to use this unit conversion to write down 2545 BTU per hour equals to 1 horsepower. This is cancelled by this one. So then you are left with 56.58 horsepower. So this is our answer, part A. And let's do the part B. The question is find out the temperature of the source. Okay, let's see for the source. Since this is a Carnot cycle heat engine, we can use this. Look, we just learned about it that this is the thermal efficiency of Carnot cycle engine 1 minus TL over TH. So I can use this formula 0.75 1 minus TL is in Rankines, which is 520. So it is 520 divided by TH. 2080 Rankines. Let me zoom out to show you how I solve this problem. So this was the question about the Carnot heat engine. I try to explain. If you have understood this question, please type in yes. If not, you can ask your professor the question. Jake says yes, Sarah says yes, Elsie says yes. Okay, let's go to the next chapter. We have finished this chapter and I have uploaded all the homeworks. Make sure that you practice those homework problems for the test. So I'm going to start chapter 7 now. So what is entropy? Entropy is like measure of disorderness. Like if you are not having some available energy to perform some work, this is entropy. Okay, entropy of the system and surrounding, the big picture is that whenever there is a heat transfer, so suppose if you have a heat engine, okay, if you have heat engine or the refrigerator cycle, so when there is a heat transfer here and heat transfer here, so when there is a heat transfer, then there is an entropy change. So entropy is known as the measure of disorderness or measure of the non-availability of energy to perform the work done. So I will explain it further in our coming slides that the second law of thermodynamics defines the quality of the um, engine or the refrigerator as known. That quality is not represented by the entropy. Okay, remember the entropy as I mentioned earlier. Let me show you. Did I mention isentropic process? Yes. Isentropic process, a reversible adiabatic process. You see, let me explain to you in our houses, they are perfectly insulated, not very perfect, but still we have some insulation on the drywalls. So we want to have a no heat transfer from our room to the environment. We don't want this heat losses. If it is perfectly zero, then we have a constant entropy process. But if it is not zero, there is an entropy increase. Entropy always, when increases, means we are increasing the disorderness, or there is non-availability of energy. We cannot perform some work now. So let me show you in slide by slide. It looks a little bit difficult, but I tell you, this is not a difficult chapter. When you understand the basic concept, then the chapter is easy. Okay, you will learn about second law. You have applied the second law of thermodynamics, new property, entropy, to quantify the second law effects, establish the increase of entropy principle, and calculate the entropy changes, examine a special case idealized process called isentropic process, derive the reversible steady flow work relationship, isentropic efficiencies, introduce and apply entropy balance. So these are the topics which you will study in this chapter. Okay, this looks intimidating, but I tell you what the big picture of this one. As I mentioned, okay, what is clauses inequality? Okay, in a cycle, this is a cycle. This circle, like integration and a cycle. In a cycle, the heat transfer per unit temperature is either equal to zero or less than zero. What it means that, let me show you. So what it means that when the heat is transferred, you lose heat. When you lose heat, this becomes negative. And in a cycle process, like in a cycle, suppose this is PV diagram. Okay, this temperature is this process 1 to 2, 2 to 3, 3 to 1. This a complete cycle. Initial and final states, they are the same state point. So in a complete cycle, you either lose heat, that's why you have a negative sign, you lose heat, or if this is a perfectly reversible process, there is no losses, like perfectly insulation, then you do not lose heat. You see my point? So either, look over here, in a cyclic process, for perfectly internally reversible, you have a zero loss of heat. You understand my point? But if you do not have a perfectly reversible process, then you will lose heat. Therefore, you will get a negative answer. You will lose heat for a real process, or irreversible process. I would say irreversible process. And this is for reversible process. And then comes the entropy, final minus initial. So you will use this formula. So this formula is for the entropy. Uh, Heat transfer per unit temperature. And this is a Clausius inequality. We call this as Clausius inequality, which is again in a cyclic process. This heat energy, either you lose, or in case of reversible process, you still have zero equality. You don't have the you can never generate energy in a cyclic process. And in reality, you always lose energy in a cyclic process. And that's why that loss is determined by the entropy. Sometimes it is not a perfect, like it's a curve here, curve here, curve here. So Let me show you. This is the next slide will explain further what is entropy. Okay, let me show you. This is probably going to explain you further. Look over here, as I mentioned, the bold line is a reversible process. The dotted line is an irreversible process. Look, for irreversible process, irrespective of irreversible or reversible process, you have the change is zero point 0.4, but for internal reversible process, you have zero uh, energy. The quantity whose cyclic integral is zero is property like volume. Entropy is an extensive property. Okay, let me show you. Over here, final minus initial equals to this 1 to 2 or internal reversible process. So delta S equals to, this is important. This is the formula for change in the entropy. Whenever there is a heat transfer, then there is an entropy change, and you will find it out. Let me show you next slide, which is in continuation of this slide. Look, the next slide is further explaining to you. Look over here. From 2 to 1, which is a reversible process, and from 1 to 2, which is irreversible. So the Clause's inequality states that from 1 to 2, this is a irreversible process. From 2 to 1, from 2 to 1, it is a reversible process. And for reversible process, we have final minus initial entropy. And in the end, you will see this is equal to this formula. Entropy always, if you do the math here, entropy always increases. So how would you select the math from here? Like from this equation, S1 minus S2 is less than 0 negative delta Q over T, correct? This becomes S2 minus S1. It changes when you multiply the whole equation by negative. It changes the inequality sign. It's the same thing. Okay. And for a system, final minus initial entropy equals to and delta Q over T plus entropy generation. Okay. What is entropy generation? It is the total entropy of the system and the surrounding. I'm going to show you one example, then you will understand more clearly about entropy. So let me show you one example. A piston cylinder device contains liquid at 300. So let me show you. During a constant pressure process, 750 kilojoules of heat is transferred to the water. So heat is transferred to the water like it is on like a pan, and you are heating water as a part of the as a part of the liquid in the cylinder vaporizes. Determine the entropy change of water during this process. 750 divided by 300 kilojoules per Kelvin. And this is positive. Determine the entropy change. So we have found the entropy change. Entropy has increased. So let us see the next slide. This is telling us that the net change of isolated system is always greater than zero, and entropy generation is system plus surroundings. If you consider system, this is our system, okay? And this is our surroundings. When you lose heat from the system to surrounding, surrounding gains heat, the system loses heat. In the end, overall entropy, which is the generation, entropy generation, you have to consider both. Remember, system and the final change, final initial change of the entropy of the surroundings. If you add those two together, the answer will always be greater than zero. Make sure you understand this concept. It is only equal to zero. The the system and surrounding, the final minus initial entropy is only possible to zero when there are perfectly reversible processes. In those processes, we have zero loss of heat. Perfectly reversible process, this entropy generation is zero. But in reality, I tell you, in reality, it is always greater than zero. You have to add both system and surroundings. For one process could go to negative, but if you see one system, if you just consider a system, when the heat is lost from the system, then the entropy change would be negative. But on the other hand, surrounding is also uh, gaining heat. So if you add those two numbers, in the end you will see the entropy generation is positive, and it is impossible to have the negative heat entropy generation for in any case. This is impossible. Do you understand this entropy concept of entropy? If you understood this concept, please type in yes. Otherwise, I will explain it further. Let me explain it with one more example. One, this is the last example, then we will end the lecture here. And I might need two more lectures to complete this. I can finish this into uh, next week, next lecture. I can finish the slides, but I need some more. Don't worry, I will give you a lot of examples in our case. So let's do one problem. I want to show you this problem will give you some understanding about the entropy. So let's do this problem. Okay, this example is good for you to understand. Okay, look, we can understand this problem. It will clarify many basic concepts. A heat source, look, this is a heat source at 100 Kelvin loses 2000 kilojoules. Okay, this is case A, this is case B. Both sources are at 800 Kelvin, and both lose 2000 kilojoules of heat. So to the sink at 500 Kelvin and 750 Kelvin. Determine which heat transfer process is more irreversible. So you will see that, look, the low temperature, and this is a little bit, the sink has a high temperature, just a big idea. I want to show you that this, when you see less temperature difference between the source and sink, if you see the temperature difference is uh, small, not large, then it has, you will see the change in entropy would be small in this case. But this is a large temperature, it's like 300 Kelvin. Here, this is about 50 Kelvin, correct? So it's a small change. You will see in the end, I can prove it. This delta S would be large because the heat loss, the temperature difference between the source and the sink is very high as compared to the case B. But let's prove it quantitatively. We know that entropy generation, change in entropy of the high temperature of the low temperature. We will calculate the entropy for the high. So let's see for the source. QRT 2000 divided by 800, correct? We are having negative sign because heat is being rejected, so I can use the negative sign. Minus 2.5 kilojoules per Kelvin. The change at the source is minus because we are losing heat at this location. And let's see for the sink, case A. For the sink or the low temperature, what is that? Q over QL over TL is the same amount of heat, 4 kilojoules per Kelvin. Now, entropy generation says for case A, let's find out the total entropy. Entropy at the source at the sink, minus 2.5 plus 4 gives you 1.5 kilojoules per Kelvin. And we can do the same for entropy, total entropy generation for the case B, and delta SH, delta SL. In our case, this is 2000 divided by 750, negative 2.5. I want to just get, I forgot. This is 2000 divided by 750. 2.66. 2.66 minus 2.5. Yes. So you see my point, guys? This is 2.66. Finally, it is 0.167. You see, this entropy change for case B is smaller as compared to this change, which for case A. Because I told you that when you see the heat suddenly will rush to the low temperature reservoir, but here it will not rush, it will go slowly. When the process happens slowly, there is a less entropy change. You see my point? I will start from here next lecture. Thank you.